Okay, so good morning, everyone. Uh, Today we start presenting the second lecture, so we continue with what we started discussing the last week. And again, first of all, I'm asking to the chat if someone can answer, if they can hear me, if everything is okay with the audio and video, and then we can start. Okay. Okay, perfect. So let's start by making a short recap of what we have seen the last week. So we discussed about complexity. So we've seen, for example, here we have again our um, Netflix scenario of the distributed system, and we wanted to see where that basically the complexity in distributed system comes from, and what we can do to manage this. And we have seen concepts like abstractions and layering that are useful to basically deal with this complexity. We also saw challenges when it comes to enterprise data management. So here we see what we have seen the last time. So relational database and how it's difficult sometimes to couple it with other structure like the object-oriented paradigm. So plus we have a problem that when we are dealing with a huge enterprise application, we also may need to uh, have different patterns and solve different requirements. So we also have seen the concept of polyglot persistence, so using different methodologies for different purposes, also going beyond what is SQL and what are the limits of SQL for an enterprise. So today we're gonna continue with this concept. So concepts like layering and abstraction will come again very often in this lecture. And we then will see how we manage this complexity when it comes to interaction. So when we distribute the system, when we distribute components of a system, how can we interact with it? We're gonna see remote procedure calls, service-based interaction models, and message-oriented ones. And then there's going to be a part, still an interaction that's going to be covered in lecture 3. Finally, we will have an overview of what are the microservices architectures and trends to basically have an overall and also up-to-date picture on what are distributed system, what does it mean to develop a distributed architecture nowadays. So let's start by describing the monolith. So what is a monolith? A monolith is an application that it's all built together, so where different parts are all contained in the same architecture, and this has a lot of problem. Of course, there is the difficulty to scale a solution like this. It's hard when we have discussed about if you remember the example of the spaghetti code, where we had the difficulties of basically separating the concerns of maintaining and updating systems. So we discussed it a lot the last time regarding data management. So it's difficult to deal with an architecture that is completely bound together. And so this coupling makes it difficult to manage this at higher level and to go up to date with the new technologies and enhance your applications. So how can we deal with those problems? There is a solution. The solution is breaking up this monolith. So um, basically taking those parts and trying to uh, make this system easier, to make this architecture easier to manage and easier to update and to deal with. How do we do this? With honestly the same concept that we discussed in the first lecture. So decomposition, so decomposing this big monolith in in smaller services, abstraction and generalization and layering, that also concept then we're gonna also see today, but that are fundamental to solve that. Because what we want to do is to basically, and we have to do, is to hide some parts of logic when we distribute this system, when we break up this monolith, and also we need to create layers that are able to interact with each other. So what are what's the way to do that? So we can refer here to a concept that is called service orientation. So service orientation is basically an ideal vision of a world where basically the resources are clearly partitioned, and every resource is consistently represented in itself. This model can apply to an enterprise application, to a task, to a specific solution, and it's a general model. And it is the service-oriented architecture is an approach for basically separating concern. The idea is basically that the logic that is required to solve a large problem can be, let's say, better managed and constructed if it's decomposed in a series of smaller related pieces. So basically, those are services that communicate then with each other over a network using certain protocols. So this is something we need, because when we are decoupling a system, we also need to then make those systems communicate. Those elements are then loosely coupled because they're basically, their concerns are separated. So they're all, every element of the system, every service is self-contained, and it's able to have an autonomous life if you want. So you don't need to update everything if you're updating a specific service. And it's something, a concept that we also seen in the first lecture. And those are, as I was saying, bounded contexts because they're self-contained. So basically, you don't have to know anything outside of it. So basically, this is the structure of a service-oriented architecture. So it can represent a specific business activity where we have seen we have a division of concerns. We have loose coupling. So basically, we have a relationship between the services that minimizes basically the dependencies. We just have to know and be aware, a service has just to be aware of the other that exists. And they basically hide the logic from the outside world. This allows for reusability, for example, of the code, and composability, so you can compose a more complex system and architecture by putting together those different services. So I hope that up to here we have a clear idea what a service-oriented architecture is. So we said before we introduced this terminology of loose coupling, and important here is to see to look at this picture because it represents a generic interaction of elements in a service-oriented architecture. Because this is something that we're gonna see also in different, and we've seen also in different mechanisms. And basically, it talks about a specific interaction. So we have a service consumer that wants to use another service that is given by a service provider. So we basically want, I make one step backwards to explain it a little bit better. So what we want to do is to basically let services use other services or other programs. And how to do this? With the structure that is in this picture, because we have the service consumer that wants to access a specific resource or use a specific service. How to do that? The service provider has to show up, so has to be declared, and you publish information on a certain service registry with a description. So the description is a basically format that allows the coupling, allows the system to know each other. Because with this description, the service consumer can discover the service that it needs, and then they can establish a connection, and the consumer can request some services, and the provider can answer with some content, for example. So basically, what we have is an exchange of information, and we can basically develop then a communication and interaction framework that can maintain this relationship and can allow this communication between services. This is, of course, a general picture that we can, however, see in different projections. For example, here is something we're going to see soon later in the lecture. So the SOAP interactions, SOAP web service interactions. So here we have a similar structure. So we have a document, we have a way to publish a service and a way to discover it, and then there is a communication that can be, for example, through HTTP GET and POST to have an interaction with the provider and between provider and customer or client. But this is something that we can see also in REST API, which is something we will discuss later, and also on data access object. So we have a similar way of seeing this structure. And this is basically a paradigm that is allowing the communication between services, and it's basically providing us a general schema that you can use throughout this lecture to see where you can find it and how this is enforced with specific application. So we can briefly start. And we start with a specific type of interaction models that are the remote procedure calls. So just to give for the ones of you that need a recap, a small summary of what RPC are. So RPC are remote procedure calls. And the idea is to basically allow to systems and services to invoke procedures that are in different processes that can also be in different machines. So remote procedure calls distinguish two roles, client and server. The clients are the ones that invoke operations, and the servers are the ones that accept operation. So it's basically the example that we have just seen. So when a client invokes an operation in a server, is basically acting synchronously. So the client asks for a certain procedure to be executed. It's waiting for the result. And then once the result the server replies to the client with the result, the client can continue its workload and continue to operate. So basically, this was the high-level interaction, but description where you can see that there are more specific interactions. So as we said, we have a client and that requires for a procedure and a procedure that returns a certain answer. So how is this communication happening? This is happening through a series of steps and rules that are typical of the RPC procedure. So the client's calls for a procedure. This call is being processed by the stub that we will see later what it does. So it's basically creating a sort of dealing with the message that the client, let's say, delivered to have a response. There is a transport layer that takes care of transporting this message to the server that receive it, interpret it, gives a response, and send the response back to the client. Of course, how to implement this is a matter of, again, levels of abstraction. So there is the basic remote procedure call, so that has the lowest level of abstraction, where basically servers provides procedure that the clients can call, and the interface is basically of the service the sum of all provided procedures. We can, of course, add one level of abstraction. So, for example, using distributed object system, for example, Java RMI is an example of that. Here, the server provides objects that the clients interact with. The objects are basically data and methods. And as a product, it's basically fitting into object-oriented programs and is more powerful than a basic remote procedure call. As a drawback, we have a middleware that is usually more complex than simple RPC. We can go one step further and discuss about distributed component-based systems, where we have, of course, another level of abstraction. So with all the good and bad consequences that this brings. And we have the concept of components. So they're basically collections of remote objects that can be reusable. There are interfaces that are clearly defined, and the focus is basically on, in this level, on reusing and integrating those interfaces. An example is Enterprise Java Beans. So while we have the capability of reuse components across applications, on the other hand, we have to deal more with configuration. And we also have more overhead since we have another level of abstraction. The upper level is service-oriented systems. So basically, there is the Lego principle is valid. So basically, applications are built by basically composing different services. In fact, the composability is a characteristic of these systems. And example of that are SOAP plus VSTL and OpenAPI that we're gonna see later. So starting from the basic concept of RPC, we have seen that we can achieve it using different levels of abstraction. Of course, of RPC exist many variants. Those, in fact, can be language specific, so bounded to Java, for example. For example, as I was discussing before, the Java RMI is an example of that, or can be language independent. In this, there are two types that can be that can be using, let's say, plain text, usually XML or JSON, or can use binary for interaction. An example of binary protocol-oriented RPC is Google RPC that we're gonna see later, or Apache Tree. So, as I was saying before, there are several rules and steps in the fulfillment of a remote procedure call interaction. The first concept that we're going to see today is the marshalling, called also serialization. So we have an object. Here we have a person. And what we want to do is to be able to give a representation in a sort of message shape that can be understood also from the server. So the idea here is that what we want to achieve with remote procedure call is a system that, as I was saying in the beginning, is able to deal with and guarantee the interaction of systems that are also possibly seen in different machines, in different processes. And what we need to do is to give something that can be easily interpretable through and can be communicated and distributed easily. So we need a system that is able to basically give a different and uniform representation of this information. To do this, we use the marshalling. And so, for example, here we see a plain text-based protocol for RPC, for example, with the JSON. A JSON is a transformation and that can be shared between the RPC actors for the communication. Another example can be XML or can be a binary one. So when we talk about remote procedure call, as we've seen, we have a request response pattern. So we need to define the request object and the response object. The request object basically represents an RPC call and basically holds all the necessary information. For example, there is the ID, the method that is necessary here. For example, it's find by name and the parameters. The response is instead representing the result of an RPC call. So given the idea and given the method is find by name and given the parameters, we can get a response. So how can we use this this interaction model, and how we can see it in a scenario where we have to deal with retrieving, for example, information of a specific person. This is something that connects basically to the part that we have seen in the beginning. So in the beginning, I mean, in the first lecture. So it deals with retrieving data from a database. But here the difficulty is that we have to do it in a distributed environment where the process or the service that requires this information can stay on a different machine. So we need to deploy this interaction. So the first thing to do is to basically deal with accessing the database, and we have seen the last time how to do that. The next thing that we have to deal is when a client wants to access this information. So what we need to have is an object or a class that serves as a stub. So it's allowing us to manage as clients this interaction with a service for at whom we are requesting this particular person. So we're requesting this particular object. The stub, what does? It basically takes our request and it serializes it. So it creates a message that can be interpretable by the server, and there is their PC client that takes care of it and send it to the server. So here we see that we have already two components on the server side. So the stub that takes care of creating this message, and our PC client that takes care of sending this request to the server. On the server side, we have the same number of elements. So we have the PC server that handles this request, and the skeleton that takes care of unmarshal. So basically translate and interpret this message that can then basically be processed, the data can be retrieved, the information can be again marshaled and returned to the client that can then unmarshal the response and use it. So we can see how this is working in a SOAR implementation. Here we are seeing the stub. So we are basically our way to dealing with the database, and what we have to do here is to basically perform this find by name request. So what we're doing here is to generate a new request, and so we are basically initiating a connection with the remote RPC server. We are marshalling our request, and basically we write and rewrite and create this message and transmit it to the RPC server, and then we're waiting for the response. Once the response is received, we unmarshal it and we use it. On the server side, something similar is happening. So what we have to do here is to, first of all, unmarshal the request that we received. Here we have to deal with invoke the method on the actual remote object implementation. And then we basically marshal our response and send it back. So let's say I'm drinking. Yeah, I think I'm still the aftermath of the vaccine that COVID vaccine that I recently did. So it's good, but so what we want to, what is this title asking here is if we can generalize the stub or skeleton. Yes, this is possible, and it's possible in two ways. One is via using code templates and generation, basically, and code generation, using basically interface description. An example of this is Google RPC, gRPC, that we're gonna see soon in the next slides. And another way is instead with using dynamic proxies. Dynamic proxies are basically using two concepts that are reflection and proxy mechanisms. And we're going to see also reflection more in lecture 3. But basically, what we're seeing is here is that we are basically, the client basically calls a method A4 of the interface, and which is the service we need. And basically this whole this whole interface is basically calling the invocation handlers that deal with this method on the server side and with this service and returns the actual implementation, the actual result. So this is a mechanism that works well. It's pretty established as a technique and as a technology. And as we have seen, there are different objects that are taking care of making this process work. However, what we were saying, and I'm repeating over and over, is that here we're dealing with systems, with services that are on different systems, on different machines, different processes, and they're not able to directly communicate with each other. So what do we do if there is a fault? An exception can be thrown at any level. So the problem is that, however, we cannot propagate the error. That because this error is likely platform dependent. So if it happens on the server, it is depending on the specifics that the servers are using. So there is the need to provide a shared representation for that. How do we do that? And how can we send back this error so that the client knows that something went wrong? With error codes. And here again, we have a concept of abstraction and generalization coming because we have error and we have specific errors that are basically generalizing or abstracting specific and platform dependent faults that happen, for example, on the server side. So here, for example, we have a list of true example of true error codes for the JSON XML RPC. And those are useful because they give us basically a unique way of interpreting something that is happening on a specific platform with specific dependencies, and that we actually, if you would receive it using a complete different platform, we will not be able to understand. So we need also unique representation of errors. So that said, the last part that we basically didn't talk about is the tunnel that we saw at the bottom of the explanation of the image representing the RPC, which is how that is the transport medium. So how are we able to transport messages? Usually, HTTP is used. HTTP works very well with JSON or XML oriented protocols, and it's basically easier because it's something we understand better. It's easier to deal with, and it's also easier to develop it, and returning something that we can better understand when we implement it in this way. However, being a high-level transport mechanism include overhead that we would avoid using TCP or UDP. However, here we have to deal with the fact that those protocols have very rigorous specification, and so we need to be able to deal with it. So it's not straightforward, but on the other side, it gives us potentially better performances. So here we can see a most general scheme of remoting patterns. Here again, we have, if you can recognize it, here we have also, again, the theme of generalization. Because basically the general structure that we've seen can be translated into something that includes a client proxy that has a requester service that basically creates a request, and the handler takes care of transmitting it. There is a medium for transport this message that is then interpreted by a server that invokes a specific service or gets a remote object and returns the result. So when we have the general picture, now we can go to see how things are really implemented. Here we have an example with gRPC. So gRPC is basically around the idea of defining a service, specifying the methods that can be called remotely with their parameters and the return types. On the server side, basically the server implements this interface and runs a gRPC server that basically is able to handle the calls that the client gives. So here we're using protocol buffers. Protocol buffers are mechanisms that are used for serializing structured data. So the protocol buffer data is structured basically as messages, where each message has basically a small logical record that contains basically information with a series of name value pairs that are called fields usually. So what we can see here is that we have a greeter, service greeter. We have a RPC connection where this is called say hello, where we are giving one request, defining the interface for the request, and in return we have a reply. There are also other methods. So for example, you can have a stream of requests and return just a hello reply, or one request and have a stream of replies, or streams of requests and streams of replies. So those are the different interfaces for methods, basically for interfacing services. And as you can see, basically here we have the request and reply methods that contain basically the fields that we need for the for the definition of them. Here we have the name, and basically the field is paired with a unique number, and those are numbers that are basically used in the binary format to identify your field. So they should be kind of unique and should not be changed where when your message type is in use. So those are representing basically the fields in the binary format. And basically what this is doing is through a code generator, creating a platform independent representation of this service that then creates our stub and our skeleton and allow basically the communication. So with this, we have finished to discuss the first part, where we defined the remote procedure call. Another way to define interaction is through service-based models. Our service-based are basically taking the concept of web services. So a web service is a software system that is basically designed to support machine-to-machine interaction over a network, and as basically an interface that should be interpreted by machines. So this brings us back to this service-oriented architecture that we have seen before. The advantage of web services is that they promote development of loosely coupled distributed system, because RPCs are basically tightly coupled to the underlying system, and this basically is not allowing them to have a good abstraction layer, a good abstraction between the function that are in the system and the external API. So we have seen before about how those functions are required, how we need to deal with them. So there is not a clear separation. With web services, the goal is to have a more loosely coupled interaction. And there are basically two different types. One is what is called big web services, and we're gonna analyze SOAP and WSDL. And there are also RESTful web services. There is another paradigm, let's say. So here we can see in this slide how the first model works. So the SOAP and WSDL. Here, the concept is similar. As I was saying in the beginning, we're gonna see it through all the lecture. The concept of a consumer and a provider, and the discovery of a service, the publishing of a service, and the communication, because there is a service provider that is that has a service that can be used. What it does is using a SOAP message to publish its information in a registry. The document that describes this this service is the WSDL, that we will see later how it's structured. Then, basically, the consumer can discover or find the particular service. And the interaction here is happening using the UDDI, that stands for Universal Description, Discovery, and Integration. And it's basically a discovery protocol that allows to find the service that's needed. Once this is happening, the binding, so the service, basically consumer, binds to the service provider by sending a SOAP request, so using SOAP message request to request for this service. So basically, those SOAP, that stands for Simple Object Access Protocols, are applications that are self-contained and modular, and are basically described by those WSDL documents that gives an interpretation, provides an interpretation of what they do. So a service is published to this UDDI. It's found in the UDDI, and it's bound and invoked using SOAP. So here we see basically the self-contained structure and the application that we've seen, and the general structure that we've seen in the beginning. So how is a SOAP message looking like? Uh, on the other side, what we have is uh, mm, is transported basically, and here is using HTTP, for example, and inside it we have basically an envelope, the SOAP envelope that basically indicates the start and the end of the message. Then we have a header that basically includes the attributes that are needed to process the message. And then the body. The body basically holds the XML data, and it is basically to be sent, and it contains all the information required for the services. So having a closer look, even if this image is can look a little bit messy, we can see how, and this is also showing the complexity of using this kind of interpretation, but we can see a WSDL document describing a web service. So here there are in WSDL, there are four main types that are useful for providing the information that are needed. One is the type. So basically, the ones that define basically the data types that are used by the web services. The message information that basically define the data element that are needed for each operation. The port type that define basically the operation that can be performed and the message that are involved with it, and the binding that are basically giving the information regarding the protocol and data format for each port type. So here, for example, we can see that the types are described, and so for example, if we want to look at the delete customer response or create customer response, just looking at the delete customer, we have a specific message that has this name, and it's specifying basically the data elements that are included here. And then looking at the port type, we have basically how how this is working, and what basically are the inputs and outputs that are needed, and the message associated to it. So another service-oriented interaction model that we are going to see today is REST. REST stands for Representational State Transfer. And it's basically a set of information that and specification that we can need to have remote communication between services. So what is not a specific protocol, is not a standard, and not a particular technology. It's more as an architecture style for distributed system that provide basically patterns that emphasize the use of certain protocol and standards. Those protocol and standards can be HTTP, for example, for the communication with its verbs and standard codes, the use of XML and JSON data representation, uniform resource identifiers, and MIME resource types. So here, for example, we can see the definition of the uniform resource identifier. And in general, what we have is basically two uh, two two types of parameters regarding an URI. So a URI is basically identifying uniquely a specific instance for a certain resource type. And every object has basically usually two parts. One that is invariant, and some attributes that are invariant, and other that are instead temporal. So we can see it in the different parameterization, because we have, for example, the path parameter that, for example, here we're trying to access a specific, like basically listing the repository of a user. And here we have the path, so the stable part. And then we have the query parameters. So the query parameters represent the temporal ones. So everything that may change should be reserved for query parameters. This allows us to have this representation of resources and of specific resource types. This this URI basically gives us an object that is basically returning a specific resource. So REST APIs share specific characteristics. First of all, they're based on a client-server architecture. Second of all, they're resource-oriented. So a media type, so the MIME type, is basically a standard that indicates the nature and the format of a document. Usually is, for example, text/HTML, text/plain, application/JSON, image/JPEG. So basically consists of a type and a subtype in the simple way. Then another characteristic is addressability. So using a unique resource identifier, you have a unique way to address and find these resources. You have a uniform interface, so permitting basically a uniform way to interact with a basically given server, regardless the device or the application type. And here, for example, in REST, we're using HTTP. We have statelessness. So basically, each request from the client to the server must contain all the information. So the server doesn't have to store client context between requests, and everything is carried by the request itself. So basically here we can see that also decoupling the client and the server as much as possible, REST can allow for a better abstraction than RPC, for example. And then the final is layering. So here again, we see this concept of layering. And here what it means is that REST is basically allowing you, client, not to see what's the actual service that you are accessing. So for example, you can deploy the API on one server, store data on in another one, authenticate the requests in a third one. And what the client has to see is a uniform interface, so that we could not be able to tell whether it's connected directly or through an intermediary system. So, for example, API gateways are a way to redirect, for example, to actual services. As we said, with REST, we have a uniform interface, that is HTTP. Why a uniform interface is important? Because with this, we can get basically guarantees when we are manipulating resources. So we can get guarantees of different types that are given by the structure of this HTTP interface. So here we see the four main verbs that are get, put, post, and delete, and those have specific characteristics. One characteristic is the one of some operation for being safe. So that means that they are not changing anything on the server side, and this is basically intended purely for retrieving data. So for the get, in fact, is the only one that has a safe flag true. Another characteristic is idempotency. So an idempotent operation means that you can do this operation many times, and you will have the same effect as doing this operation just once. So, for example, get is idempotent because reading multiple times and reading one time should give you the same result. Same goes for put and delete operation, where is not true for post, where you basically create a new resource. And then there is the body. So basically, in principle, every operation is allowed to have a body. In practice, it's just used for put and post. And we can see that basically this is allowing us, this system, to have a set of operations with certain guarantees that can be easily understood and easily implemented. Another advantage of that is the availability of status codes and error codes. This is basically connecting to what we have seen before with RPC, when we needed to have ways to manage faults. Because here, using unique description of errors, we can immediately know what is happening. So we have a sort of a structure and representation of errors that are maybe happening on our side or on the server side, And with GDP, you basically even have ranges. So you know that, for example, 200s are positive responses, 400s errors means that there is an error from on the client side, 500s is from the server side. But giving this unique interpretation is also allowing us to understand better what is happening and have a sort of generalization of certain specific errors that happen in the server, where we don't know how this is implemented, we don't know anything, but we have a clear representation of what is happening. So when then basically specifying this style, we have basically same specification goal as big web services. So what we want to do is to define message types, define endpoints, the return times, and whatever. And we can see API with JAX-RS. This is basically the API that Java provides for specifying RESTful web services. It basically uses plain old Java objects, so POJOs, and annotations to basically specify how a Java API can work. This is again basically is providing an interface, and there are different applications, one of which is Jersey, another one is Apache CXF, that implement this concept and allow us to actually deploy RESTful web services using Java. Another concept that is interesting is the one of OpenAPI specifications. So that were formerly known as Swagger specification, and it's basically an API that describes the format for REST APIs. And basically, an Open API file is allowing you to describe your entire API. So it's basically used to generate the documentation that you need, and that basically allow you to add a sort of form to your API that you can have implemented, for example, using one of the JAX-RS implementations. So the question here is, we've seen that there are different ways to model interactions, and what should we use? Is REST better? Because in the beginning we said, okay, REST is going towards more loosely coupled interaction, and well, RPC seems something that it's more complex, needs a more specific interaction. So what is better? REST is not always good, of course, for all the applications, as well as RPC can be a pain in specific ones. The difference is basically where the design effort is has to put in place. In RPC, you have to invest more in the scripting, in describing the interface, in the interaction between protocols, and to understand basically all those concepts like serialization, how to reference a remote object, what's the granularity of the methods that you have to define. Well, in REST, the effort is more on defining media types. And basically, there is not a specific answer. You can even combine multiple styles. In fact, you're gonna see it in this assignment. The idea is the same idea that we have seen in the first lecture, that there is not a general answer, and it depends on what your application requires. So going for one or the other can allow you different can basically serve different purposes. If you need something that is more lightweight, maybe you need to go for REST. If you need something that is more safe and more secure, maybe you want to implement RPC. But it's really something that you have to adapt to your application and to your requests. Okay, another way to specify interaction is through message-oriented models. They start from a specific need. So remote procedure calls as we have described in the beginning, they start by having a synchronous structure. So the client sends a request and it stays there waiting for the response. However, when dealing with distributed system, asynchronous messaging is fundamental, because we need to decouple not just in the space, so not just decouple the system, but we also may want to decouple in time. And so we don't want to let all the services wait and be even all active at the same time. So basically, messaging allows us to deal with this information. And um, given their characteristic, allows us basically to develop a system that doesn't require the server, so and the client, so the provider and the customer to be basically up and ready again all together at the same time. So one of the main concept is the primitive of the queues for messages, because the queues are basically collecting the messages that can then be interpreted and uh, basically dealt with by the receiver. And this is important because it's basically allowing a system where either the receiver or the sender can be passive during the interaction. Of course, there are different primitives that allow to do that. So there is the put to add a message to the queue, the get, and to to get the message from the queues, the poll to check if there are new message or the notify. If basically the system gives you information when a message is added to the queue. So an application needs to consume messages. So what we want to achieve is a system where we send events in a form of messages, and those events are basically consumed and interpreted by an application. So how can application consume a message when it's ready? The easier way to do this is using polling mechanisms through the concept of message consumers. So there is a consumer that basically takes the message, interprets it, and actually, as the word says, consume it. But how to check when we have messages? So the easier way to do it is through the polling mechanism. So the polling consumer is checking iteratively on the pipe or on the queue if there are new messages. This is an easy way because you can set basically your timer so the application can be active every minutes, certain seconds or hours. So the application decides autonomously basically through the polling when to get new messages. So this is positive. And on the other side, it's not very efficient because this means that the application can be active searching for messages even though there are no messages in the queue. There are no messages that have been delivered. A solution for this is to go to event-driven consumers. So with this way, we're solving another question. So how to automatically consume messages as soon as they become available. So how to do this? We can do it both two methods, like so the blocking method get, or using an asynchronous way of notify, so receiving a notification where a message is provided. So we may, however, want to send those messages to exactly one receiver. So basically rebuild a sort of RPC system where we have a single customer and a single provider. How to do this? This is achievable through the point-to-point channel. So either this the receiver, so either the provider receives the message or no one does. So this pipeline is the easier way to achieve that. However, we want to maybe deal with these messages, so we deal with these events in a concurrent way, because messages arrive sequentially. However, dealing with those sequentially can be really slow. And this can create also bottleneck in the system, because you can still fill the queue with messages and requests that can never be response, because the operations and the consuming of these messages is still happening. A way to solve this is to define competing consumers. So there are more consumers at the receiver side that are basically taking these messages. And usually the way those messages are distributed are through a round robin, but there can be different implementation that are possible. One can say, why are we not using multiple channels? Why are we not use multiple pipes? The problem is that if you define multiple pipes and you have a unique consumer for each pipe, you may have the case that some pipes can still represent a sort of bottleneck, while other can be instead empty because no message are arriving. So having a unique pipe and using this mechanism can solve this problem as well. However, there can be another problem in addition to that. So how to send a message just to receivers that are interested to it. So to do this, there is this paradigm of the publish subscribed. So basically every subscriber here is notified if a particular event that they're subscribed to is arriving. How are the ways to let this subscription happen? Those ways are two, mostly. One is basically listen to specific topics. So a topic-based publish, subscribe paradigm. So the message is sent together with a specific topic, and the subscribers that have these specific topics will receive this message. Another option is to basically using filters. So the subscriber filters for specific content and use that to interpret and consume the message. This message-oriented interaction brings to definition of a message-oriented middleware. So basically, a communication channel that contains messages that are representing units of information. There is many ways to achieve that. There is Hive, there is RabbitMQ that you're going to use in the assignment, there is Kafka. Some of those we're going to see more in lecture 5. But what's the idea of this middleware? The idea is to have a channel reduction, because potentially when we have distributed system, we can have many technologies, many messages format, and we may have a channel and a communication for between each element of the system. The message-oriented middleware is reducing this complexity gain. So the concept of reducing complexity by, however, adding an additional component. So here is the same concept that we have seen different times and many times. So we're adding another component, but this component is taking care of basically dealing with the messages and allowing an easier representation and a more, let's say, loosely coupled uh, interaction between systems that can be finally distributed both in space and time. How to send those messages? So there are different protocols, MQP, for example, STOMP, MQTT are example of that. And the differences between, for example, MPQ and STOMP is that STOMP is more analogous to HTTP, but they share a similar structure. So they provide a message header with some properties and a header and a frame body that includes the message. So the general idea is still to have a basically header with some generic properties and the body that contains the message. RabbitMQ, as you will see also in the assignment, is a kind of a broker that allows for basically a multi-protocol polyglot, again, messaging system. Here again, we can see the same concept of polyglot that we have seen for persistence in the data, but for messaging, because RabbitMQ, what it's doing is to basically allow to send and receive messages using different protocols and make all those clients communicate with each other basically transparently without having to deal with different communications. So again, we are adding complexity. Again, we are adding another level, but we are basically decoupling more and more those systems that don't have that have to know less about each other to communicate. So this brings us to the end of the lecture. So we have seen in the beginning that we wanted to break this monolith. So we wanted to find a way to have self-contained systems that were loosely coupled and distributed. But this is something that we achieved during time. And here, this is slide I like the most because as an Italian, of course, it makes me feel home. But the idea is that we have add in the time different ways to deal with complex systems. So in the beginning, of course, not having information and not having inefficient communication and networks, the implementation were very confused. We had this spaghetti-oriented architecture where everything was staying together, allowing poor isolation, allowing poor maintainability, and all the problems that we have seen until now. Then we were able to basically layer this monolith in different conceptual applications, but still with the limits of having everything on a single structure. Lately, where we're going to is to basically have different self-contained systems that are working independently and that they communicate with each other over the network. So the microservices allow and introduce better separation. This is of course allowed by the fact that we have advancement also in technology, so faster communication, more efficient, better protocols, better ways of serialization. So again, we see this image that tells us that basically through this implementation is allowed to go more and more to a service-oriented architecture in the ideal way that we have seen in the beginning, where everything is separate and self-contained. So better separation, is it always good? Of course, has a lot of advantages that we discussed through the first two lectures, but however, introduce a problem that is defining the boundaries. Because how to make a system self-contained where there are different dependencies between the elements. So, for example, here we're taking the example of a music corporation database, and we want to achieve a separation and a better separation of this system. That also means a separation of the of data and of information that can be accessed by any specific service. And we need the concept of boundaries, because the concept of boundaries is, as if you remember what we've seen in the previous lecture, is what allows a transaction to make everything happen in one time or roll back if there is a specific problem. We define for example, how to define the boundaries of a specific transactions. However, how can we deal with the fact that, for example, we have two different services that refer to the same data, because this is the problem when you have, for example, foreign keys. So here, what you should do is to basically break this foreign key relationship, basically stopping this finance code from reaching this table, and create a communication between those two. This is, of course, allowing better isolation, but it's also increasing the number of calls that you have to do to access the information, because you need to access the catalog, and if you need to access this information from the finance, you need to request the catalog to access the DB, get a response, and then deal with it. So while a perfect separation of concerns and a self-contained system can be good, you have to think on how to make those things communicate, and what's the cost of having separate concerns. Especially because when we communicate, we want to make the service communicated, we end up to the problem that we've seen before also in the message-oriented middleware. So we have a lot of communication interactions between all the elements, and we need to deal with that. So a solution can be to have a single API, for example, that basically makes it possible to communicate, to let all the systems, all the services, all the microservices communicate with each other. And basically what they're doing, if you see in this picture, is to hide the basically internal microservice architecture from an outside consumer. That can be, for example, a web app or a mobile app, and contain and basically create an abstraction to everything that is below in terms of architecture deployment. However, it's a single entry point. This single entry point can become what it's called a chat interface, because it has to talk to many services with different protocols. It can become as well a bottleneck. So how to deal with it is potentially to divide the API in order to handle different services and allow just a better communication and better interfaces to deal with the underlying architecture and to communicate with what's beneath. So this is just to show you that, of course, separating concerns and using concepts like abstraction and layering and decoupling is good, and can be positive for many applications, but also you have to deal with the complexity that comes with it. So, as coming back to the question, a question that was present the first time in the first lecture, what to use is always dependent on what you need in terms of complexity, in terms of distribution. So you will have the chances with these assignments to check better and deal with different technologies, but it's interesting to look at this implementation in a critical way in order to understand what's better for your use case. So with this, I'm done. If there are questions, I'm happy to answer. Otherwise, see you the next week. Then, goodbye and see you the next week.